Hello again. This is our number 25 lecture for Wednesday the 15th. Wednesday the 15th. And before I start getting into the formal notes here, I'm going to tell you a secret. It's a secret. Remember this? Also known as y equals mx plus b. This was the generic form for the equation of a line. And all the lines you could possibly draw, they're not much different from each other. What's the difference between one graphed line and another? How much it tilts, or what direction it tilts, which was controlled by m, the slope, and where it's located on the grid, where it goes through the y-axis, which was controlled by b, also known as the y-intercept. Now we're looking at equations that are, when we get to the very end of today, the equations are going to look like this, and the graphs of these are dependably always parabolas. Parabolas look like this or like this, and instead of just two controls like slope and y-intercept, we're going to have really three controls: the a, the h, and the k. And the h and the k are going to tell us where this important turnaround point is, also known as the vertex of the parabola. The a is going to tell us a couple of things. It's going to tell us whether the parabola opens upward or downward. And it's also going to tell us, does the parabola look kind of spread out like that, or is it more, say, narrow and pointy like that? That's what the effect of the A is. H and K will locate the vertex. Okay? Now let's pretend I didn't say any of that stuff and start from scratch right here. We're first going to look at quadratics of the form, very simple form where it's just y equals plain old x squared plus a number, which could be a positive or negative number. So we're looking at these three for comparison to start with: x squared plus 3, x squared minus 5. There's the functions listed again. Here's some voluntary x values, which I just picked for ease of use. And here's the computed y values. To save time, it's all filled in for us. So over here, I'm going to graph first the f function, which was just x squared. And at negative 3 squared is positive 9, which would give us a point right there. Negative 2 squared is positive 4. Negative 1 squared is 1. 0 squared is 0. Positive 1 squared is 1. Positive 2 squared is 4. And positive 3 squared is 9. So there's what that looks like, and I'm doing the best I can to make it look not like a letter V, but it's a parabola. The graphing calculator does a lovely job of drawing these. Your freehand, it's a little tricky. But there's the parabola representing f of x equals x squared. Let's take a look. What's the domain for f? Domain is, of course, all the possible x values, all the allowable legal x values. And the function here is just square the number. We can square any number in the universe. There's no worry about dividing by 0 or square root of a negative or anything exotic. So the domain is negative to positive infinity. This graph, if I had more room, I could go to the left forever, I could go to the right forever. Okay? Now what about the range? Range is all the possible y values, and you see that the y values could go up forever. Pick a larger x, you get a larger y, but there is a bottom, and I didn't do a very good job of locating that, but that's supposed to be at 0, 0. The lowest y value we ever got for this was at 0. The range here starts at 0 and goes up to positive infinity. So I'm going to write square bracket 0 to positive infinity. Remember, infinity or negative infinity always gets a round bracket because there is no last number. Square bracket indicates there's some last number or first number. Okay? Let's try the g function. The g function, you square each x and then you add 5. So, negative 3 squared is 9, and you add 5, you get 14. These numbers are all these numbers with a 5 added on, if you stop and think about it. So, let's go over here. Now, I can only show this and a little part of the table in the camera at once, but at negative 3, the table says, negative 3, we'd square that and get 9 and add 5 and get 14. So at negative 3, instead of 9, we're up here at 14. That's 14 on the y-axis. And at negative 2, we're at 9, which is right there. And at negative 1, we're at 5. I'm sorry, no, we're at 6. 3, 6. And at 0, we're at 5. And then on the other side, at positive 1, we're at 6 again. And at positive 2, we're at 9 again. And at positive 3, we're up to 14 again. So here's the graph for the g function. Well, why don't I label these? This was f, and this is g. So, what effect does the plus 5 at the end seem to have? If you look at the first graph, think about adding 5 to every y value. What it physically does to the graph is it pushes it up 5 units. It moved the vertex up 5 units. Okay. How about the domain? The domain is the same because we can square any number we want and add 5. The domain is still negative to positive infinity. Now the range is different, isn't it? The range now continues to go up forever, but it never gets below this y value, which was 5. So the range is 5 to positive infinity. Okay. And now we're going to do h of x, which says x squared, square the x, and then take away 5. So when we square negative 3 and get 9, 9 take away 5, we get 4. Square that, you get 4. 4 take away 5, we get minus 1, and so on and so forth. So let's draw that over here. At negative 3 for x, we've got positive 4 for y. At negative 2 for x, we've got negative 1. Then at negative 1, we've got negative 4. At 0, we've got negative 5. And then we start seeing like a mirror image. These things are symmetric, right? At 2, we're back to negative 1. And at 3, we're back to positive 4. And draw that in there. Nice and careful. So there is the graph for g of x. And again, you see it's the same exact shape. They're all parabolas. If we could cut them out or draw them on tracing paper and put one on top of the other, if they're drawn accurately, they should be exactly the same shape. They're just in different places on the grid. The minus 5 seems to have pushed the original graph, the plain old x squared graph, down 5 units. So the domain is the same, negative infinity to positive infinity. Now the range goes all the way down to negative 5. We can get as low as negative 5. We can get as high as the imagination goes by going far enough to the right or to the left. So the range is negative 5 to positive infinity. Okay. Now I want to show you something about the calculator here. This may be a rerun, but that's okay. Some of you might have been absent. If we want to do the table using the calculator, first you turn it on, then you at y equals, and let's say if I put in that first thing, the first function was x squared, I'll type in x squared. Well, let's do the second one. First one wasn't very interesting. X squared plus 5, okay? Then, if you look above the window key, you see table set. Table set is what that's short for. If I push second and that, now I get to choose where the table will start. So it's set at 0 right now. I'm going to leave it at 0. And this is read really delta table, which means how much do you want your x values to change by? Do you want to go 1, 2, 3, or you want to go 10, 20, 30, or do you want to go 0.1, 0.2, 0.3? Whatever you want the x values to jump by in the table, you can enter there and it'll be automatic. Now for the independent variable and the dependent variable, keep those both on automatic most of the time. And now if I hit second and table, see there's the input, and that would be the independent variable, and then the output, the dependent variable. This is x squared plus 5, 0 squared plus 5, 1 squared plus 5, 2 squared plus 5, and so on. If I want to see the negative part of the table, I just use the up arrow. So where I started doesn't really matter that much, except I wanted to make sure I started on an integer. So I can go as far to the right or as far to the left as I want using the up and down arrow. Okay, and just to show you this other thing, how this works a little better, supposing I put 1 divided by 2 there, and then go back to the table. See, now it's going up 1/2 at a time. If I wanted to get those in-between values for some reason, I could do that. You can, sky's the limit, folks. You can put whatever you want there. You put whatever you want there. Good power tool for making the table. Okay, now down to here. We're going to look at this form of a parabola or quadratic equation where it's got something being subtracted from the x value before the squaring happens. So we're going to compare, again, plain old x squared, and then x minus 1 in parentheses squared, and x plus 2 in parentheses squared. The table's been done. Of course, you could churn out the table with pencil and paper in your brain if you really had to, but use the calculator and you get this fairly quickly, and it's all filled in, so that's going to save us some time. So let's go over here now. I'm going to graph the f of x again, which means at -3 for x, we get 2, 4, 6, 8, 9 for y. At -2, we get 4. At -1, we get 1. 0, we get 0. 1, we get 1. 2, we get 4. And 3, we get 9. So there's the plain basic, what a lot of textbooks call the parent graph. The mom and dad, the parent graph for all the other quadratics. Okay, that's f. Now g of x, x minus 1 squared, at -4, oh, you know what, this went further and I didn't bother. Well, that's okay. At -4, for g of x, we're all the way up to 25. Go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, right there. At -3, we're at 16. So that's 24, 22, 20, 18, 16, right there. And then at -2, we're getting a y value 9. And at -1, we get 4. And at 0, we get 1. And at 1 we get 0. And at 2 we get 1 again. And then at 3 we get 4 again. And at 4 we're back up to 9. Now if I connect these points as carefully and neatly as I can, and compare this G graph, it's getting a little crowded already. Compare the G graph to the F graph. Notice it's the F graph shifted 1 unit to the right. See, every X value had 1 subtracted from it before the squaring process, so it took later to get to the same Y value. We had to get up to 1 before we got 0, as a for instance. Anyhow, the -1 inside the parentheses shifted the graph 1 unit to the right. And let's say right now, go back and report on the domain and range. The domain, of course, we could take any number in the universe and square it. We could take any number in the universe, take away 1, and then square it. So the domain is the same for both of these. In fact, before we even draw the graph, can we do this for any number you can imagine? Of course, you can take any number, add 2, and then square it. So the domain there will also be negative to positive infinity, all real numbers. How about the range? Both of these have the lowest Y value 0, and they both go up forever. So the range is the same for both of these. It's 0 with a square bracket to positive infinity. Okay? Let's look at the H function, where you add 2 to the X value first, and then you square it. So at -4, at -4 for X, we get 4 for Y. And at -3, we get 1. And at -2, we've got 0. And then at -1, we've got 1. So that's coincide. Let me start drawing this now so it doesn't get confused later, because it's getting crowded. At 0, we're up to 4. And at 1, we get a 9. And at 2, we shoot all the way up to 16. And at 3, we get all the way up to that value, 25. And then the next number in the box in the table is 36, and that would be off the grid, so we'll go that far. And what's the physical effect to the graph of having that +2 in the parentheses? It pushed the original f of x graph 2 units to the right. So the range is, again, 0 to infinity. Get that out of the way. Here's how we boil things down. And I know it's confusing at first, but you will get used to it after you've done enough practice exercises. The h in the x minus h squared will shift the graph to the right h units if the h is a positive number. In other words, like when we did take away 1, we took away positive 1, it shifted the graph 1 unit to the right. And it will shift to the left if the h is a negative number. Like if we do this shifted to the left, didn't it? But the x plus 2 could be rewritten x minus -2 squared. Seeing the -2 being subtracted, thinking of it that way, 2 boxes to the left. Okay, so as it says here for another example, take away -5, we wouldn't write that usually. We'd write +5, but that would shift the x squared graph 5 units to the left. Okay, so that's the end of very long, 20 minutes long, page 1.